All right, today we're looking at section 11.4, the cross product. And this is the sort of background for it. So many applications in physics, engineering, and geometry involve finding a vector in space that is orthogonal to two vectors. Here we will study the product that will yield such a vector. It's called the cross product. Okay, so we talked about the fact that orthogonal means perpendicular. If it's orthogonal to two vectors, it has to be perpendicular to two vectors in space. And it's unique if that's the case, right? It's a unique orientation and so forth of that. So we need some matrices. Do you guys remember matrices at all? Have you learned about matrices before? Yeses or nos? Some yeses. Has anybody not seen matrices before? One? Okay. So we might need to talk a little bit one-on-one if what we're doing is not working for you. Matrices are an organized way of listing the coordinates of lines. This is where you usually encounter it the first time. Algebra 2 is the first place they'll show up generally. They may not have shown up in your Algebra 2 course, but that is generally the first time you would ever see them. And so that would have been high school, okay? And you find them in systems of equations. So in systems of equations, you're trying to solve for x and y. And so if you're doing x and y, you have two equations and two unknowns. And you use substitution, you use elimination. And matrices is the third option, and it's not always discussed. For example, if you didn't do them before and you did calculus or college algebra here on campus, we don't always get to matrices. There's just so much material in a college algebra course that it isn't always taken care of. But it's one of the topics that should fit into a college algebra course, okay? So we're just going to look at some details. We're not going to go through the whole gamut of what do matrices do for us, but we're going to talk about them very specifically for what we need them for the cross product. So we're specifically looking at what's called a determinant for a matrix, okay? So the determinant for a 2x2 matrix, and the determinant has matrices, instead of writing the whole matrix, you just see these sort of absolute value kind of bars on either side of it. That means determinant. Is actually found, and again, y'all know that I'm a visual kind of remembering person, by multiplying this diagonal together and then subtracting and multiplying the other diagonal together. Okay? That's how we find a 2x2 determinant. Those are pretty straightforward. 2x2 determinants. You multiply one diagonal, subtract, multiply the other. A 3x3 determinant is not that straightforward. So the determinant of a 3x3 matrix is a combination of three 2x2 determinants. So here's what we do. We isolate, and what this definition is doing is isolating the top row. Okay? So you see the A1, A2, A3. And A1, A2, A3 show up in front of each of the other three determinants. That's where they went to. Okay, so we see where A1, A2, A3, we're good with that part. Now I want to talk specifically about one of them at a time. We're going to do A1. So when we take A1, we sort of cancel out the row and the column that A is on. And we get the other four pieces down here that we find the determinant for multiplied by A1. So the A1 in the top left-hand corner, and it's the four pieces in the bottom left, A1 in the top right-hand corner. No, I said it right. A1 in the top left-hand corner, and then we have the four pieces in the bottom right-hand corner. Okay, so let's talk about the middle. Whoops, meant to delete that, so let's try again. So in the middle, the opposite sign, so we have the opposite of A2, right? Subtraction for A2. And in A2, again, we eliminate the row that A2 is on and the column that A2 is on, and we get the other four pieces. So we have B1 and C1, and then we have B3 and C3. That's the determinant that's formed. And then we do the same thing with A3. So when we do A3, it's back to addition, so the signs alternate, positive for A1, negative for A2, positive for A3. So when we do A3, we eliminate the row A and the column 3. And we get the bottom left-hand corner of this matrix. Okay? Once we get to those individual pieces, we do the same thing we did on the previous slide, where we multiply through the diagonals. So you can write out a formula for this in terms of A's and B's and C's and the subscripts. But I don't think that's nearly as helpful as remembering the imagery of how they come about and looking at your diagram each time. So I'm choosing not to write them out, but if that helps you, you feel like that would be a more beneficial way to think about it, your book shows that, and you're welcome to look at the formula that it creates using these multiplication factors instead of using the determinant imagery, okay? So we're going to do an example, one more definition, and then we've got an example. So if we're looking at two vectors being multiplied, so all of this is just with numbers, right? A1 through B3, through C3, excuse me, it's all numbers, it's just coefficient numbers. Over here, we see the vector component. So you see ijk is the column on the top, right? So the ijk comes to be in the front, positive I, negative j, positive k. And then we have the 2 by 2 determinant of each of the different locations in space, right, in the diagram that you don't have for the row that you're on and the column that you're on. So I has this bottom corner right here. And j has these two pieces right here. And K has this bottom corner over here. Do you have a question, Adrian?
I was just saying, like in physics, we learned like you go down diagonally for each row and then back the other way. Is that viable? Would we allow us to use that here too?
You mean like this?
Mm-hmm.
And then up?
Yeah.
Yeah, that would be the same imagery. So you did this one, and then you go down the diagonal over here, and then back up.
All the way up to the V2. Yeah.
It wouldn't be V2 though. It would be the V3.
Sorry, you're right.
Okay. Yes, you can think about it from that perspective, of course. It would be the same thing. So your imagery is just looking a little bit different, but the values you're going to get would be the same. Mm-hmm. So if you did this one, then you're down this diagonal and back up. Yeah, you can do that. Okay. You got to do one. It's all well and good until you actually practice one and see how it goes. So you'll see that there's several things. We're going to do U cross V. We're going to do V cross U. And then we're going to do V cross V. Okay, 3 parts. Are we ready? Okay, so part number 1.
So it's different depending which vectors first?
It is. Well, at least we're going to explore whether it is.
Oh, okay.
Yes, that's the question. There's a relationship, and we're going to figure out what that relationship is, Adrian. Okay? All right, so U cross V. And so I'm going to set up the 3 by 3 determinant to start, because again, that's what we're going to keep going back to in terms of how we set the rest of it up. So we're going to have these diagonal, or this matrix. We're going to have I, J, and K at the top. That'll always be the top. And maybe we won't set it up like this every time. Maybe we'll jump to the next step. But for this first one, I'll set it up like this. And then we're going to put row U, or U on row 2. I should say it that way. U is 2, negative 2, 0. And V is 3, 0, 1. Okay, everybody good so far? Lovely. So we have our I, and then we have the determinant that's in the bottom corner, which is negative 2, 0, 0, 1. We have J. So J is 2. Sorry, it's not plus J either. It's minus J. Let me get that fixed since I noticed it. Minus J. 2 and 3, and then 0 and 1. And then plus K. And K is 2 and negative 2, 3, and 0. Now, this sort of beginning step where I put them in the I, J, K, and the U and the V, you could just jump to this over here. If you can see it well without that, that would be fine. Or as Adrian mentioned, if you write this piece down and then you skip the next step because you know how to move through the diagonals, that's fine. But somewhere along the way, there should be some kind of work about how we're setting it up. Okay? So I've got all those pieces. And then we're going to have I. And then we're going to multiply. So we're going to multiply down and then back up. So this is negative 2 times 1. That's negative 2 minus 0. Back up. And then minus J. We're going to multiply down and then back up. So 2 times 1. Is it 1? Yeah, it's a 1. So 2 times 1, which is 2. Whoa. 2. And then minus the 0, which gets multiplied back up, and then plus K. K is actually 0 when we multiply down, and then it's minus negative 6. I'll write it in there just to be clear. Or plus 6 at the end when we multiply back up. And if we simplify a little bit of the multiplication and so forth, I have negative 2I minus 2j plus 6k. Oh, and the good news is it matches my notes. It's always nice. Okay, everybody good with that? All right, let's try B. B is the opposite order, so we're going to do V cross U and see what happens. And at least for this problem, maybe all the problems, I'm going to set them all up. So I, J, K, and then my rows 2 and 3 flip. So I have 3, 0, 1, and 2, negative 2, 1. 2, negative 2, 0, sorry. I think I got them on there right. Okay, so we have our I is 0, 1, negative 2, 0, minus J, 3 and 2, 1 and 0, plus K, and it's 3 and 0, 2 and negative 2, I think. Does that look right to everybody? My piece is okay? And I'm definitely out of space, so we're going to see if we can make it a little smaller. And so I have I, multiply down, I have 0, and then I have minus negative 2, and then I'm going to do minus J, and I'm going to have 0, minus 2, and then I'm going to have plus K, and that's going to give me negative 6 minus 0. All right, so minus negative 2, I have a plus here. So I have 2i. And then I have minus j and times negative 2, so this is plus 2j. And then I have minus 6k. So what does it seem like happened when we did u cross v versus v cross u? The sign switched, right? They're additive inverses, right? Like they're a negative. One's a negative of the other one. So that's going to be one of our properties in a minute that we're going to write down. And we've established it, at least in one case example, but it is a true statement for all. Our last one that we're supposed to do here is v cross v. There's also a property at play there that we haven't seen yet that we're going to see as we do that one. Do I have space on another slide? Let's see. I don't. So we're just going to make this smaller. One more time. And that's good enough. Okay, so this is C. We're going to do V cross V. And we're going to set it up again the same way. So we have I, J, K. But V is 301, so it gets listed twice. 301, 301. So we have I, and then we have 0101 minus J, which is 3311. Plus K, which is 3030. Okay, so let's see what happens when we do these. So we have I, and then I have 0 minus 0, minus J, and I keep putting absolute values there, I have 3 minus 3. And then I have plus K, where I have 0 minus 0. All right, so what happened? Every single one's a 0, right? So this actually ends up giving us the 0 vector. So when we cross a vector, with itself, v cross v, the same thing would have happened if I did u cross u. I get back the 0 vector. Now that's a little bit interesting, right? That you would actually operate on yourself and you get back 0. It's actually like those are somehow inverses of each other to get back to 0. So these are the properties that we see at play, the algebraic properties of our cross product, some that we've explored already, others that we haven't. So the first one is one that we just established. U cross V is the negative of V cross U. The other one that we established is number 5, U cross U is 0, the 0 vector. The other ones we didn't explore, but we could. I just wanted to show you some of them and not all of them, right? So if I do U cross V plus W, that's the same as U cross V plus U cross W. Scalar multiples, so that looks like a distributive property, by the way. Number 2 would be a distributive property, right, of a vector crossed over addition. C is a scalar crossed over the product or the cross product, right? So C over U cross V, and it's the same thing as C times U, then cross V, or C times V and then cross U. So we've got the associative kind of property going on. Number 4 is a zero property. So it kind of should make reasonable sense that if you have a row of 0, because that's what's going to happen in those determinants if I'm crossing something with 0, that I'm going to end up getting back 0. Right? I'm going to end up multiplying everything by 0. I'm going to get zeros. So not only is U cross U 0, but U cross 0 is 0. So it's not a unique thing that you get when you cross it. You might get 0, or you would get 0 in both cases. And then the last one talks about the dot product interacting with the cross product. So when we have the dot product of V cross W, this is the same as having the cross product with V dotted with W. That would take a little bit more work for us to actually see how that's playing out, but it is our 6th property. So these are algebraic properties. So we've got the algebraic properties, and then we also have geometric properties. So there are 4 geometric properties. So our geometric properties have to do with this, or have an additional piece to do with this angle theta that's happening. So U, V, and W are non-zero vectors. Angle theta is the angle between them. So U cross V, when we cross those, we find what we were supposed to be looking for as a whole point. The point of finding a cross product is finding orthogonals. So when we do U cross V, we find the vector that is orthogonal to both U and V. So if you want a vector orthogonal to U and V, you find the cross product of them, and that's what you will find. And I want you to envision the corner of the room, because I think it's a pretty good picture. It's a very contrived picture, or we can do we'll do the brown, no, let's do the corner of the room. Let's do the top. Okay, so if we have one vector that's coming out across this wall, right, it's just the line that's formed with that wall, but imagine there's a vector coming out that way. And we have a vector coming out across the front of the room. Can you kind of picture sort of vectors extending in those 2 diagonals, right? Then the vector that's orthogonal would be the one that's coming down the wall, right? It's forming a perpendicular angle with both the right-hand wall over here, my right, your left, and the front of the room. So it's orthogonal or perpendicular to both of them at the same time. And it's unique. It's found by the cross product. The next one here, sorry, that looks like it got extra on there. It's messed up on my paper. That if you take the magnitude of U cross V, it's exactly the same as having the magnitude of U times the magnitude of V times the sine of theta. This establishes how we can find the angle that is between two of these, right? So we can find this angle by finding the cross product's magnitude and then each of the individual magnitudes and doing a little bit of algebra with those and trig simplification for the theta. U cross V is equal to 0 if and only if U and V are scalar multiples or they're parallel. So that should sort of play into why it is we're seeing that if U cross U, or that when U crosses, when we do a U cross U, we get 0 because we're parallel to ourselves. We're a scalar multiple of ourselves. So of course we're going to get 0. And the fourth thing is that the area of the U cross V's magnitude is the area of the parallelogram that has adjacent sides U and V. So the picture that's formed there is something like this. If I have, let me make them vectors. If I have this as U, and then we have an adjacent side, here's V. So here's U, and here's V. And we form a parallelogram with those, which would mean that we would extend the parallel side here and the parallel side here. We would create a parallelogram. This area inside is actually equivalent to the magnitude of the cross product. Okay, and you know how to find magnitudes. Anytime you have a vector, you know how to find magnitudes. They're always found the exact same way. Okay, the square root of the components squared. All right, so we're going to find a few examples that find a few of these things. Okay, is everybody good? Okay, so far. Okay, yeah.
That's a quick question back on when you're having the different
Algebra.
properties of the cross product. Number 2, wouldn't it not just be easier just to add the 2 and then do the cross product? Like,
Yeah.
It seems like it adds like extra steps by doing the cross product of both vectors.
So I don't think that they're trying to tell you that doing it one way or the other way is preferable. But provided that you might have one of those pieces of information already, it still might be more helpful to do one versus the other. So if you remember what happened in class last time when you guys were up at the boards, there were places where you were like, I need to do 3 times these things. Well, but you found that you already did the dot product, so multiplying by 3 after you did the dot product was preferable. Well, that might not necessarily be preferable if you hadn't already done the dot product, right? And so I think there's some of that going on here, that these are just different options for finding things, and there might be a particular reason to use one or the other. Yeah. Okay. On this one, we're going to find U cross V and V cross U, which we're not actually going to calculate both things now, right? Right? Because we have a property that says that if I calculate one, I can very quickly get the other one. Yeah? Okay, so that's important. And then B says that we're going to show that it is orthogonal. We're going to show the corner of the room description that I just told you. We're going to prove that it really works. And the way that we prove that it really works, well, we'll get there in a second. Let's do it one piece at a time. All right, so the first thing is that we're going to find U cross V. And I'm going to write the matrix up here at the top. So, or the determinant for it anyway. So the determinant for U and V, so we're going to have I, J, and K. And then U is -1, 1, 2, and V is 0, 1, 0. Okay, so far so good? Sticking it all in there. So U cross V then is going to be, and that's what we have up here. I'll write it to the side. So let's write it out component-wise, right? So I have I, and I is going to be multiplied, and this I'm going to not write down my middle step now, kind of like what Adrienne was suggesting before, and I'll come back up to my diagram and hopefully we can catch it. So we're going to multiply these two together. If I make my arrows long enough, I can delete them. That's why they look funny and be extra long, okay? I'll be able to delete them and we'll be able to move on to another one. So if I do this, I'm going to have 1 times 0 is 0 minus 1 times 2, which is 2. Then I have minus j. So if I do minus j, then I'm going to do these sort of longer ones like he had mentioned. So I have -1 times 0, that's -1. And then I have minus 2 times 0, which is 0.
-1 times 0 is 0.
Oh, I'm sorry. Moving too fast. Thank you, Connor. All right, 0 minus 0. Now I have k. All right, k then. We'll multiply this one and then this one. And so then I'm going to have -1 times 1, that's -1. And then 1 times 0 is 0. Are they okay now? Yeah? Okay. All right, so this is -2i minus 0j. I'm going to write it for the moment, but feel free to leave it off if you wish. We're just going to be doing some calculations with it, so I want to see the 0. Just a preference thing for me. And then I have minus k, or you could write minus 1k if it's helpful. Okay, so I have -2, I have 0, and I have -1. This is the ijk form. The vector form would be -2, 0, and 1, if you wish. Okay. Is that okay? Oh, that's only one of them. That was U cross V. We can do V cross U really quickly. So what is V cross U?
2, 0.
Yeah, 2, 0, 1. I didn't. It is 1. I missed a negative over here. Thank you. There's my negative missing. Okay. I've got U cross V at the top. I've got V cross U underneath. Okay, are we good? All right. Part B says we want to show that it is orthogonal to U and to V. Now, do you remember how we can show the two vectors are orthogonal? It is not something we did today. You could calculate the angle between them. That's more than you need to do. But it is possible you could do that and it would be 90 degrees. Right, Dylan? Sure?
Wasn't it U times V over the magnitude?
Nope. Nope.
Equals 0.
Okay, I want you to grab out your notes from 11.3. want you to look through it. We saw something about orthogonal in 11:3.
Oh, dot product.
So what does it
Dot
say,
product is
Adrian?
zero. When the dot product of the vector v.
Okay. So when a dot product of two vectors is 0, they are orthogonal. Okay? So we have u cross v, and we want to show that it is orthogonal to u, and that it's orthogonal to v. So we're going to find the dot product of this vector we just found, and you can do u cross v or v cross u, doesn't matter which one, okay? You're going to find the dot product of this vector we just found with u, and then you're going to find the dot product of the dot product of the vector we just found with v. So we're going to find v cross u. I'm going to do u cross v, but u cross v, and we're going to find its dot product with u, and we're going to find u cross v that we just found's dot product with v. Okay? So we're going to take the first box that we found over here, and you could do the second one if you want. I'm going to do this one, -2, 0, -1. And I'm going to do the dot product of that with vector u. So vector u was back up here. Here it is right here. So I'm going to have -2 times -1. I'm going to actually really write it out. Plus 0 times 1 plus -1 times 2. That's the dot product with u. It's going to create a scalar, remember. So I have -2 times -1. That's 2 plus 0 minus 2. And what do we get? 0, as expected, right? And then we're going to do the same thing. We're going to take that -2, and we're going to dot product it with the vector v. -2 times 0 plus 0 times 1 plus -1 times 0. That one's even more straightforward than the last one because each of the components are individually 0. When I multiply them out, I get 0. Okay, so these two pieces tell us that u cross v is orthogonal to u and v. It checks out. We found the vector that came down the wall, in essence, and we were correct when we did the dot product. It gave us 0. So then, we're going to find a unit vector on the next one. We're going to find a unit vector that is orthogonal to u and v when u is 3i minus j and v is 4j plus k. So, in finding a unit vector, you know how to find a unit vector, right? What do you have to do to make a vector into a unit vector? You just divide it by its magnitude, right? Okay, so we're going to find the cross product that we did before, right? The orthogonal business. We're going to find that cross product, and then we're going to find the magnitude, and then we're going to do a division, just like before. So we're going to set this up again in our vector form for u cross v. I, j, k. So I is 3, j is -1, and k is not present, so it's 0. I is not present in vector v, so it's 0. J has got 4, and then the k is 1. So to do u cross v, we're going to have I, and then the vector up here, going like this, is going to be -1 times 1 minus 4 times 0, so it's minus 0. Minus j. So we've got 3 times 1 minus 0 times 0 is 0 plus k. K is going to be over here. 3 times 4 is 12. There's our biggest number so far today. And 0 times 1 is 0. And we end up with -I minus 3j plus 12k. I believe. Okay. And then we're going to find the magnitude of that u cross v. Okay, so it's the square root of each component squared. So this is -1 or 1 squared, -3 or 3 squared, and then 12 squared. So 12 squared is 144. 3 squared is 9, and 1 is squared is 1. So 144 plus 10 would be 154. And I don't think it simplifies. Yeah.
For the tests, you don't mind if we leave off a negative when we're squaring it?
Not in the
Square root?
slightest,
Okay,
because
just wanna make sure.
because when we square it, we're gonna get positives every time. So I'm fine with that, with us recognizing that along the way. So here's my magnitude. How do I find a unit vector then?
Will be the cross product of the,
Don't need a cross product.
just the vector.
Unless, say it again, Dylan. Maybe I misheard you. Say it again.
I said the cross product over the magnitude.
Yes, that's right. I'm sorry. I heard you say find the cross product, and we already did that. So that's the part I was confused about. You're right. It will be the cross product over its magnitude. So that square root 144 will be in the denominator of each of those coefficients. If we think about writing this in unit vector in the component form, I have -1, -3, 12. And so this one, the unit vector, would actually be each of those divided by the square root of 154. And if I rationalize, I will get negative square root 154 over square root 150, over 154. And then I will have minus -3 square root 154 over 154. And I will have 12 square root 154 over 154. Okay, is that jump okay? Where I didn't actually show the step before in the rationalizing? We're all okay with that? Okay. One more question.
Does it matter if we simplify? Because like the 12 and the 154, we can take
Oh,
this out.
that one we should. And actually the 3 and the 154 does as well. That's a good catch. Adrian, let's do that real quick. So yes, let me make this smaller. Oops, that's not going to do it. Let's try one more time. So yes, we should make those values reduced if we can. The first one doesn't do anything. That is to say, it doesn't simplify at all. But 3 and 154 both do. So what's 154 divided by 3? Does it? Oh, it doesn't. No, it doesn't. I was thinking about 54, not 154. It doesn't. The last one does, though. My apologies. 12 and 154 both do simplify. They both divide by, do they divide by 4 or just by 2? Just by 2? Yes, they do just divide by 2. So this is 6 and, is it 77? Is that right? 154 divided by 2 is 77? True? False? True? Okay, good. So I have 6 square root 154 over 77.
I have a question about that.
Yep.
Will there ever be a situation where it matters if it's U cross V or V cross U?
You mean for the purpose of finding like this? No.
Okay.
And the reason is because because vectors that are scalar multiples of themselves are identical. They're the same
Gravity just
vectors.
creates a line.
They just create a different direction, like the 180 degree opposite direction, if you think about it that way. Yeah. Okay, one last question. We're going to find the area of a parallelogram that has the vectors u, I, j, k, and v, that is j plus k, as adjacent sides. Okay. We had part of a theorem that talked about area of the parallelogram. What did it say the area of the parallelogram is?
The cross product of the magnitudes.
It's just the cross product, right? And then we have the magnitude of the cross products, which I think is what you were saying, right? The magnitude afterwards. So we're going to find the cross product, and then we're going to find the magnitude of that. So when we see area of the parallelogram, this is kind of like in Calc 1 where we have multiple ways of asking you to do the same thing, right? Find the derivative, find the slope of the tangent line, find the slope of the point, right? All those things, and they all mean the same thing. The same thing's happening here. Area of the parallelogram means we're finding the magnitude That's not a good word. Let's try that again. Magnitude of the cross product. That's what we're finding. So we're going to find the cross product, and then we're going to find its magnitude. Because I've written above there, I'll write this down here. So we want U cross V, and that's going to be the determinant I, J, K. So I, J, K is 1, and then it's 0, 1, 1 for for V. And then we will write it out over here. So this is I. So multiplying down my diagonals over here, and then back up, I have 1 minus 1 plus J. So J multiplies on the outer diagonals. So we have 1 times 1 is 1, and then 1 times 0, so 1 minus 0. And I've got the plus sign happening in the middle there again. How about a minus? And then plus K, and K would be along these diagonals. So I have another 1 times 1 minus 0. I'm off screen. Let's try again. There we go. So I ended up getting, again, I'll write it as 0i, but you could leave it off. And then we have minus j and plus k. Is that correct? So we have the vector negative j plus k. And in order to find the actual area of that cross product, we find, well, the area of the parallelogram created by that, we find the magnitude. So we'll have the square root of, again, you don't have to write the 0 squared, but I did for this, and then 1 squared and 1 squared. So what is the area of this parallelogram? Square root of 2. It's not very big. Yeah. And that should kind of make sense. I look back at the vectors themselves. Their components are all 1s. And if you were to draw this in space, which we're not going to do the space drawing for it or whatever, but you would see that square root of 2 coming about just like when you have like the diagonal of a rectangle, square, a diagonal of a square with side lengths 1, it's the square root of 2. It would look much the same as that in terms of the imagery, right? We've got those diagonals showing up. Any questions? All right.